Last lesson in chapter 3 today. This is one of my favorites. Okay, so today we're going to compute and interpret the correlation coefficient for linear data. We're also going to look at residuals to help us decide if a fit is good or not. We're also going to distinguish between correlation and causation. Okay, you will see this stuff if you do anything with statistics. Okay, a lot of fun stuff in this section. So this is 3-6, analyzing lines of fit. So what is the equation of the line of best fit for the data in the table? Well, we saw in the last section that it's kind of a pain in the butt to do this by hand, because it all depends on how well you draw your line. Well, we can do all of that with technology. Okay? A linear regression is a method used to calculate the line of best fit. A line of best fit is the trend line that most closely matches the data. Okay, so if you're following along in the textbook does it through the graphing calculator. I think it is a million times easier to use this on Desmos, and you're allowed to use Desmos on the air test. So we're going to go ahead and do this with Desmos. Okay, so step 1, you're going to add a table and enter your data. Okay, so that's step 1. So here's my data. Okay, so I'm going to use the internet, and we're going to go to Desmos. Okay, so hang on, let me just put my computer around. Right, so I'm going to pull up the internet. I'm going to minimize it a little bit so that I can actually see my data without going back and forth. Okay, so I'm going to type in desmos.com. You're going to go ahead and click on Graphing Calculator. Okay, so the first thing we need to do is add a table. So to add a table, you go to the plus sign. Okay, and look, table. Okay, so let's put our values in for x. So we have 1, 2, 5, 8, 9, and 17. Okay, then we put in our y values. Okay, we got 30, 55, 75, 120, 145, and 250. You can do this on your phone as well. Okay, so Desmos actually has an app you can download. It's free. Or you can go to online and then click onto Desmos. Okay, so I have this, I'm doing this obviously on my computer, so it's very easy for me to pull up the tab. Okay, so, okay, I've got my dots. Notice I can't see them, however. Okay, so I'm going to change my scale until I can find them. So one thing you can do is use your mouse to scroll, but that'll take forever because I gotta go all the way up to 250. So to do this, you can click on this the wrench, and the x-axis, okay, we can see where we go from. So we go from 1 to 17. So what if we start at 0 and we go to 20? Okay, and then if I look at my y's, I have 30 to 250. So let's go a little bit lower, so 25 to how about 255? That way we can see everything. Oh, look, there's all of our dots now. So yay. Okay, so there's our table. That was step 1. Step 2, we want to perform a linear regression. So underneath your table in the next line, we're going to enter y1 tilde mx1 plus b. Okay, and I'll show you 2 different ways to do that. Okay, so see how we have a 1 here? We're going to go down to 2. So we're going to type in y1. Okay, literally type in the button y1. And we're going to do tilde. Okay, on my computer, it's shift, and then the button right above tab is how you get the tilde. Okay, so that's how I can find it. Or if you can't find it there, if you click on the keypad, if you go to functions, change it to stats. I lied, not stats. Where is it? Okay, well, it should be with stats. I don't know, maybe I can't see it. Huh, maybe they only do it where you don't have a keypad. Weird. Okay, well, anyway, you're going to hit shift and the button right beside 1. And then we're going to type in mx1 plus b. Okay, y equals mx plus b. That's what we're looking for here. Okay, so that gives me this entire line. Okay, so if we look at our statistics, we have something called r squared, and we're going to talk about that in a little bit. Okay, r, E1 with our residuals, that'll come up shortly. It tells us what m and b are. So this equation is actually y equals 13.56x plus 17.59. Okay, y equals mx plus b. Boom, there's m, boom, there's b. All you have to do is type. Okay, so really cool. Values of m and b are given. We can also click on the line and drag to see different points. So if I click anywhere on the line, notice I can move it and the points change. So, oh, I know exactly what some points on this line are. Okay, so very cool there. Okay, so then we just write the equation of the line of best fit. Okay, so y equals, remember, mx plus b. So y equals, m was this 13.56, and I'm rounding, plus b, 17.59. There's my equation of the line of best fit. Super quick, super easy. Okay, your turn. Use linear regression to find the equation of the line of best fit for the data in the table. Okay, so you should be opening up Desmos on your computer tab or on your phone, whatever you're working with, and pause the video and try this, please. Okay, so I'm going to do the same thing. So I'm going to get rid of all of this stuff, so you just have to hit the X in the corner and it goes away. I'm also going to reset this to go from -10 to +10, just so we can kind of get a back feel to where we were. Okay, so I'll reset everything really quick. Okay, so the same thing. We're going to add a table. I'm actually going to minimize so we can see the points. Okay, so plus table. So I go 1, 2, 4, 5, 7, 8, 9. Okay, my y values, I got 5.4, 6.1, 8.1, 8.5, 10.3, 10.9, and 11.5. Okay, if I go back to my graph, okay, I can just drag this a little bit because they're all pretty close. Do my linear regression, y1 tilde mx1 plus b. There's m and there's b. So let me minimize this and we can write the equation. So you should be getting y equals 0.77x plus 4.69. That's the equation on the line you should have. All right, so this is on to correlation coefficients. Okay, so what does correlation coefficient reveal about the quantities in a bivariate data set? Okay, bivariate, the prefix bi means two, so we're working with two variables. That's all that means. So when you perform a linear regression using technology, you're also given the correlation coefficient. The correlation coefficient, which is represented by the letter R, is a number between -1 and +1 that indicates the direction and strength of the linear relationship between two quantitative variables in a bivariate data set, okay, which again just means a set of data that uses two variables. Okay, so big things to know here. We're between -1 and +1, and it tells us the direction and strength. Okay, those are the two most important things in that paragraph. Okay, and also it goes by R. So here's our three different kind of where it falls. So if our correlation coefficient is close to 1, so for example here, R is 0.984. Okay, the closer it is to 1, the stronger the relationship. Okay, so this one is really close to 1. So this is a very strong correlation. Okay, notice R is positive, it's not negative, so it's a strong positive correlation. Okay, so as the values of X increase, Y increases. Okay, if I'm close to 0, okay, so for example, -0.284, doesn't matter if I'm on the negative side or the positive side, whenever I'm close to 0, that means there's a weak correlation. Okay, so we think about the last lesson, that means there's no relationship. Okay, weak correlation, there might be a teeny tiny bit, but not really enough to say so. Okay, there's no correlation. And finally, when our correlation coefficient is close to -1, okay, so our example here, -0.995, that's really, really close to -1, it means it's strong, okay? The closer we are to those endpoints, the stronger it is. Okay, and since R is negative, that means we're going to go downhill. So there's a strong negative correlation between the two variables. Basically, as X increases, Y will decrease. So we're going to find, well, so we're given the correlation coefficient. You need to tell me what it tells about the data. Pause the video and try letter A, please. Okay, R equals 0.1. That's really close to 0, so this is a weak. And notice it's positive, so we say positive correlation. Okay, pause the video, try letter B, please. R equals negative 0.6. Okay, 0.6, and that's kind of in the middle, so we're going to call that moderate. Okay, and it's negative, so it's a moderate negative correlation. Okay, so we actually can see this in Desmos. Okay, I still have that last example up. Notice right here, R equals 0.9975. What does that tell us? Well, this line of best fit is really, really good. Okay, it's super close to 1, so we have a very strong positive correlation in this example. All right, so then that leads us to residuals. A residual is the difference between the y value of the data point and the corresponding y value from the line of best fit. Okay, we call that the predicted y value. So to calculate your residuals, you do the actual y value minus the predicted y. Okay, predicted value again is the y value you get when you plug the x's in to your linear regression. Okay, your linear regression gives you an equation. All we're doing is stuffing our x's into the equation. That gives us our predicted y. Okay, so what do residuals tell us, or what's the point of this? Well, a residual plot shows how well a linear model fits the data set. So if the residuals are randomly distributed on each side of the x-axis and clustered close to the x-axis, then the linear model is probably a really good fit. Okay, so two things, randomly distributed on either side. Basically, that means you need to have an even number of points above the x-axis as you do below the x-axis. Okay, and the closer they are to that x-axis, the better. Okay, that's what we are looking for. Cool thing is, Desmos also does this. Okay, so if I go back to Desmos, okay, right down here where I have the y1 approximate mx1 plus b, right here it says residuals. Let's hit the plot button. Notice it gave me in another column here. Okay, my residuals. So they took each x value and plugged it into the equation we got down here. Then subtracted this minus that value, and that's how we get the residuals. So if I look at the residuals, I have 1, 2 below, I have 1, 2 above, and I have about 1 or 2 right on the line. So we are pretty good above and below. Okay, also notice they are extremely close to this x-axis. Okay, they are very, very close. If you have ones that are way up here, it's not going to be a good fit. Okay, these are extremely close and it's balanced above and below. So this is a good residual plot. So we have a good fit. Okay, I'm also going to show you how to calculate this by hand because the air test will give you problems like this. Okay, so student enrollment at Blue Sky Flight School over 8 years is shown. The owner used a linear regression to determine the line of best fit. Okay, the equation the owner came up with is y equals negative 35x plus 1,208. We want to know how well does this linear model fit the data. Okay, so we need to find the predicted value. So we are going to use the equation that the owner came up with. Okay, so y equals negative 35x plus 1208. Okay, so my first x I'm going to plug in is 0. So y equals negative 35 times 0 plus 1208. Okay, we get 1208. Okay, we're going to plug in 1 now. Y equals negative 35 times 1 plus 1208. Okay, so calculator work. Negative 35 plus 1208. We get 1173. Okay, now we're going to plug in 2. Negative 35 times 2 plus 1208. Okay, so negative 70 plus 1208. We get 1138. Okay, we're going to do 3. Negative 35 times 3 plus 1208. We get 1103. Okay, plug in 4. Okay, see how, well, this is very tedious, but it's not hard. Okay, so negative 35 times 4 plus 1208. We get 1068. All right, plug in 5. Get 1033. Okay, plug in 6. 998. Plug in 7. 963. Okay, tedious part's over. Okay, to find our residual, we do the actual y value minus our predicted. So I'm going to take this column, my y's, minus the predicted. That's how we get the residuals. So 1235 minus 1208 gives me 27. 1178 minus 1173, that's just 5. 1115 minus 1138, negative 23. 1102 minus 1103 is negative 1. 1020 minus 1068, negative 48. Okay, 1050 minus 1033, we get 17. Okay, 1003 minus 998, we get 5. And 978 minus 963, we get 15. Okay. So then the book says, okay, after we calculated all this stuff, we plot it. Okay, this is what it would look like plotted. So the residual plot shows the residuals randomly distributed above and below the x-axis, and they consider it clustered somewhat close to the x-axis. Linear model is likely a good fit. I personally look at this and I say, okay, we've got, let's see, 5 above, 3 below. That's not too bad. That's pretty balanced. But in my opinion, I don't think these are all that close. Okay, 27 away, negative 48 away, those are pretty far. So it's probably a decent fit, but it's probably not that 0.99 that we really want, right? So that's how you would calculate those. Okay, so here's a problem to try. Okay, so pause the video and try this, please. Okay, so y equals 1.44x plus 877. I am plugging in 0 through 7. Okay, so if I plug in 0, I get 877. If I plug in 1, I get 878.44. If I plug in 2, 1.44 times 2 plus 877 gives me 879.88. If I plug in 3, I get 881.32. If I plug in 4, I get 882.76. If I plug in 5, I get 884.2. Almost done. Plug in 6, I get 885.64. If I plug in 7, I get 887.08. Okay. So now I'm going to do y1 minus the predicted. Okay, so y1 is right here. So 832 minus 877 gives me negative 45. 872 minus 878.44, get negative 6.44. 905 minus 879.88, I get 25.12. Okay, 928 minus 881.32, get 46.68. Okay, 903 minus 882.76, get 20.24. 887 minus 884.2, 2.8. Okay, 863 minus 885.64, negative 22.64. And 867 minus 887.08, get negative 20.08. Okay, so if we compare these, I got 1, 2, 3, 4 negatives, 1, 2, 3, 4 positives, so that's a good balance. And I think negative 45, that's 46.68, those are pretty far away, but it's not horrid, so this would be a pretty decent fit. Okay. All right, so example 4, we're interpolating and extrapolating. So the graphic shows regional air travel recorded by a domestic airline company. How can we use the data to estimate the number of air miles people flew in 2003? If the trend in air travel continues, what's a reasonable estimate for the number of miles that people will fly in 2030? Okay, so they want us to plot the data points and then do a linear regression. Okay, so we just did that with Desmos, where this video is already long enough, so I'm just going to skip ahead. We get the values y equals 47.87x plus 1345.04. Okay, so that leads us to the definitions of interpolation and extrapolation. Interpolation is using a model to estimate a value within the range of known values. Okay, so notice my years started with 1975 and go to 2015. Since 2003 is in between those, we're interpolating. Okay, if I want to estimate 2030, we're going to use extrapolation. It's outside the range of known values. So you just plug in those values. Big thing you got to be careful with is X is the years after 1975. So you would have to do 2003 minus 1975 and plug in 28. Same thing over here, you plug in 55. Okay, and so number 4, pause the video and try this. Okay, so we want to find how many were in 2012. So 2012 minus 1975 is equal to 37. So I know that's what X is. Okay, so Y equals 47.87 times 37 plus 1345.04. Okay, 47.87 times 37 plus 1345.04 gives us a total of 3116.23. Okay, that's the number of miles people flew on the airline in thousands. Okay, example 5, correlation and causation. A student found a positive correlation between the number of hours of sleep his classmates get before a test and their scores on the test. Can he conclude that he will do well on the test if he goes to bed early? So causation describes a cause and effect relationship. A change in one variable causes a change in the other variable. So to determine whether two variables have a causal relationship, we actually have to do an experiment, okay? Because otherwise there's too many unknowns that might affect it. So we can never determine causation without doing an experiment. Okay, other variables, like in this problem, maybe the time you spent studying or the proficiency of the content, that could affect how well you do on the test. Okay, so going to bed early does not cause you to get a better grade. It might help, but it does not cause it. Okay, another example, lifeguard notices the outside temperatures rises, the number of people coming to the beach increases. Can we conclude that the change in temperature causes more people to go to the beach? Well, did we do an experiment? No. So we cannot say that the temperature causes people to go to the beach. Okay, same thing there. So that is all about 3-6. Okay, a lot of fun stuff in here, a lot of statistics. Okay, homework tonight, you're on page 133. You're doing problems 8, 10, 13, 15, 16 through 19, 22, and 23. Okay, please come prepared with questions. We are actually going to do a project with this stuff, so I hope you guys are excited. Have a great day.